Okay, today's topic is what is a Skew T diagram? We need a way to graphically depict the vertical structure of the atmosphere, focusing mainly on profiles of temperature and humidity. We need to do so in a way that is easy to grasp visually. We also want our chosen depiction to be useful for quantitative analysis, and I cannot begin to list all of the ways in which Skew T diagrams are useful for quantitative analysis. Although there are other options for displaying atmospheric profiles and doing the kind of analysis that we'll be talking about later, the Skew T log P diagram, which is often just called a Skew T for short, has become the depiction most widely used in operational and research meteorology. For context, a weather balloon or radiosonde is released from the surface by a weather observer. This happens usually twice a day at 00Z and 12Z at hundreds of stations around the world. And it's the basis for basically taking a snapshot of the atmosphere's structure so that we can generate analyses and other products that are useful for weather forecasting. As the balloon ascends, it measures pressure, temperature, humidity, and wind direction and speed. It does not usually measure altitude directly because it can't do so accurately without specialized sensors. Pressure is the baseline coordinate for vertical position in the atmosphere. Pressure always decreases from the surface going upward because the pressure at any level is always the weight of the atmosphere above it. So it can only go down as you go up. And so it serves as a very nice reference point for where you are. From the pressure and the temperature and humidity, you can then calculate altitude if you need it using the hypsometric equation.
Yeah. Dancing that. I got it. Look out. Woo! It stopped and reeling. Oh, there you go. There it goes.
0.26 Celsius and slowly falling as you'd expect. If your goal is to plot the temperature that the balloon measures as a function of the pressure that it's rising through, then the first thing that might come to your mind is an XY type plot with pressure as the x-axis and temperature as the y-axis. Now, we would call this a pressure-temperature plot or PT plot because the pressure is the x-axis and the temperature is the y-axis. And if we plot a sounding from a sample station, in this case I picked Amarillo on the 23rd of April 2007 at 12Z, which is about 7 a.m., the plot looks like this. It's a very interesting little curve that goes from zero pressure on the left and fluctuates through various temperatures and then increases and winds up almost at 900 hectopascals on the right-hand side. In this particular kind of plot, the horizontal axis is actually a measure of distance above the surface. As we said before, pressure decreases as you go upward. And so we really want to turn this plot around so that we can visualize things as pressure being related to up and down as opposed to being horizontal. And so we can flip it like that so that temperature is now the x-axis and we have pressure as the vertical axis. And we would call this a TP plot because the T variable, the temperature, is being used as the X variable and the pressure now is the Y variable. Just as we wanted, we now have the vertical axis being related to distance above the surface, but with the caveat there that the pressure increases as you go toward the surface and decreases as you go up. The way this is currently oriented, up on the plot refers to low in the atmosphere. In fact, the surface is the top of that curve. So that's not very intuitive. We'd like a representation which is more intuitive in the sense of relating low on the chart to low in the atmosphere, high on the chart, high in the atmosphere. So let's flip the whole thing upside down and put 0 at the top and 1000 at the bottom on the pressure axis. So we have the surface at just under 900 hectopascals, and the balloon ascends toward lower pressure and gets colder as it goes up. And eventually, up around about 190 hectopascals, it starts doing other stuff, which we'll talk about a little bit later. And now we have things oriented so that up on a chart corresponds to increasing distance above the surface. There's still a bit of a problem, though, because if we look at how much space on the chart corresponds to a specific change in altitude, a fixed change of altitude at high pressure shows up as a relatively large change on the chart, whereas higher up, the same vertical change in altitude is more compressed, and if you go to the very top, you can have a 5-kilometer change in altitude corresponding to a very small change in actual pressure. So we want to correct that as well. The reason why it does this is because pressure actually decays exponentially with altitude, approximately. So if we take the logarithm of pressure and use that as the vertical axis, we will get a better, more linear representation of height relative to the scale of the diagram. So we'll change the vertical axis to logarithmic. And we'll go ahead and add extra labels above 100 hectopascals so that we have everything nicely labeled to the top. This is what the sounding looks like now with logarithmic pressure as the vertical axis. And one thing you might notice is that the temperature profile in the lower atmosphere is much more linear looking now than it was before. It used to be kind of curved. Now it's pretty much a straight line with a few little jiggles here and there. As we hoped, a fixed change in vertical altitude, measured in meters or kilometers from the surface, corresponds roughly to the same vertical height on the chart as well. Now this is called a T log P plot because we have T as a horizontal axis and log P is the scale of the vertical axis, and it's also known as an emegram. It's a type of thermodynamic diagram because energy turns out to be proportional to area on this diagram. This may not make a lot of sense to you at the moment, but when we get to a later part in the course, we'll talk about how area on the diagram is proportional to energy involved in processes involving vertical motions, changes of pressure, and so on, and that will be a very useful thing for interpreting things that happen on a Skew T diagram. I've added height markers here to show you how height corresponds roughly to pressure. Now, the exact relationship varies from one sounding to the next, but these are fairly typical of what you'll see if you look for the heights going with various pressure levels. 3 kilometers typically occurs around 700 hectopascals. 5 kilometers usually occurs at a pressure slightly above 500 hectopascals. By the time you get to 300 hectopascals, you're usually pushing 10 kilometers altitude. 100 hectopascals is around 16 kilometers. And finally, if you go up to around 10 hectopascals, which is quite high in the atmosphere, we're exceeding 30 kilometers altitude. You may have noticed that when you look at the sounding that you can divide it into two fairly distinct pieces. From the surface up to about 180 hectopascals, the temperature follows a relatively linear trend toward colder temperature with altitude. And then above that height, there's an abrupt transition to a different behavior where the temperature stays kind of the same for quite a while and then it even increases. We have a name for these two different sections. The lower section is what we call the troposphere. That's the layer in which temperature typically decreases fairly steadily with height above the surface. Then we have the stratosphere where the reverse tends to be true. The temperature may be somewhat isothermal at that point, but it often also increases on the whole. And so the overall temperature profile tends to be distinct between the troposphere, which is the layer closest to the surface, and the stratosphere, which is the next layer up. The boundary between those two layers is called the tropopause. Whenever I refer to the tropopause, I'm referring to that fairly abrupt transition between the steadily decreasing temperature profile of the troposphere and the steady or increasing temperature profile of the stratosphere. Now, the troposphere is where most weather of interest takes place. So we generally are not that concerned with things happening in the stratosphere, and there's not really a lot of reason to devote space on our diagram to things above 100 hectopascals. So usually a thermodynamic diagram will only go from 1,000 to 100 hectopascals because that pretty much encompasses the troposphere most of the time, and we don't care too much about what happens above that level. So if we simply expand the vertical axis to go from 1,000 to 100 rather than 1,000 to 10, we now get a slightly stretched vertical view of the lower part of that area as seen here. And there's the tropopause again, and the stratosphere and the troposphere. But we're only going now from 1,000 to 100 hectopascals. Once again, here are the height references for this specific sounding, about 3 kilometers at 700 hectopascals, all the way up to 16 kilometers up near 100 hectopascals. Now, this temperature log P diagram, which we call an emegram, is visually very similar to another kind of diagram you may frequently see called a Stubbe diagram, in that we have temperature as the x-axis, and we have pressure decreasing with height. It's not quite the same because a Stubbe diagram doesn't use a logarithmic pressure axis. Rather, it uses something proportional to pressure raised to a constant kappa. And for that reason, a Stubbe diagram is technically not a thermodynamic diagram. But we're not going to talk about Stubbe diagrams here. It's not really that important for what we're talking about now. But we still have a bit of an issue that we want to address. We're very close to where we want to be with this diagram, but there's something we can still do. Notice that the temperature decreases rather sharply as we go up. We're down to about minus 65 in this specific soundings. It's not uncommon to have soundings in the tropics and elsewhere where the tropopause may be as cold as minus 80, minus 90 degrees. And that means that we have to have a temperature scale that accommodates that very wide range of temperature. But that also means that you're squashing everything horizontally so that it's hard to see detail and it's hard to distinguish slopes. The way we fix that particular problem is to simply take into account the fact that temperature usually decreases with height and push the upper part of the sounding over to the right to make more room. So we skew the temperature lines to the right to make more room like this. And you'll see now that the entire sounding fits into a much smaller part of the plot. So this is now what we call a Skew T log P plot. We had a temperature log P plot or a T log P plot, and now we've skewed the temperature lines so that it becomes a Skew T log P plot. And commonly people just call it a Skew T diagram for short, and don't bother saying the log P part. This is now a convenient opportunity to give names to the curves appearing on this plot. To start with, we have isotherms, which are the lines of constant temperature. We didn't really have to name them before because we had a horizontal axis in temperature, and so you just had to look straight up from every temperature value and know what temperature you're at. Now you have to follow those isotherms to know what temperature corresponds to a particular point on the plot. And then lines of constant pressure are called isobars, and you'll see that in other contexts as well. So every black line going horizontally represents a constant value of pressure, and for any combination of pressure and temperature, we can find a point on the graph. There's a lot of wasted space in this depiction because with the isotherms now sloping to the right, we no longer have to worry about very cold temperatures occurring near the surface. They're only going to occur higher up, and the slope of those isotherms allows the colder temperatures to be represented somewhere in the middle of this plot. And so you're never going to have things happening in the far left portion of this plot. So there's a whole section we can just get rid of. What I'm going to do here is get rid of the portion of the diagram which is colder than minus 40 at the surface and colder than about minus 100 up around 160 hectopascals. So we'll just delete that and stretch everything out, and this is now a more conventional representation of a Skew T diagram. You'll see some variations in the horizontal axis, but the basic idea here is fairly common to what you'll see everywhere. Notice that because the x-axis labels no longer match the isotherms, we have to add labels to the isotherms themselves as well. With the Amarillo sounding that I've depicted here, I've only been showing the temperature, but dew point is also measured in degrees Celsius, and we can add the dew point curve as well, and that's always going to be either on or to the left of the temperature curve. So this is now, as I said, the classic Skew T depiction of an upper air observation or sounding, including both the temperature and the dew point profiles. I want to mention this excellent website that's maintained by the University of Wyoming. Their Department of Atmospheric Science has a page that allows you to browse soundings from around the world and various times, and this is a great place to go to just look at random soundings and get a feel for what soundings look like in different locations. And the Skew T diagram is one option that you have for graphically viewing a given sounding. To summarize, here's what we covered. We talked about why we need Skew T diagrams as a way to depict vertical profiles of temperature and humidity. We talked about why the Skew T diagram is laid out the way it is, and that's a little confusing for newcomers, especially with the sloping isotherms. I introduced the two families of curves that are part of every Skew T diagram and that serve as the basic coordinate system for plotting temperature and dew point. The isotherms, which are lines of constant temperature, and the isobars, which are lines of constant pressure. What I did not discuss yet are three additional families of curves that are extremely useful but require additional theoretical background to understand. Saturation mixing ratio curves, dry adiabats, and pseudo-adiabats, which are also known as saturation adiabats or moist adiabats. Those will be covered in a later module. For reference, the material that we just talked about is related to the pages shown here in the textbook, pages 18 through 21 and 44 through 47.